one question here I didn't think I really covered very well. So if you have it, what I want you to do is I'll put it up here on the screen real quick. The faster fast food example, and we kind of walk through all of that. And on the third page of that example, um, we we started out with this base case where we were testing a null hypothesis. Oops, that should be alternate hypothesis right there. Let me change that. That's an alternate hypothesis. Null hypothesis we were testing is that the percentage of customers who wait more than 2 minutes was 0.63 against an alternate that was less than 0.63. And then we looked at various scenarios here against that. We looked at just the base case with assuming a true value of 0.53, and we went through a variety of those scenarios. So let me pull up. I'm going to send you some screenshots from what we looked at yesterday. I'll send you these screenshots. This is a PDF. And this was the base case where the null hypothesis P was equal to 0.63, the alternate less than 0.63 at a significance level of alpha equals 10%, and we had 250 samples that we checked. Now, here's the thing. We can do a significance test with just this information right here. But in order to calculate the power of the test, we have to assume some value that fits the alternate hypothesis criteria. And so in the context of this question, the restaurant manager said he needed this proportion to be 0.53 to justify the additional labor for another employee. So that's where we started. And so we plug those in, and at an alpha level of 0.1, when we looked at the alternative down here at the bottom, there were about 9,700 out of the 10,000 samples that we ran, where we would have correctly rejected the null hypothesis as being and found in favor of the alternate, that the true proportion was less than 0.63. We would have, in about 97% of those simulations, we would have found that to be true. And that's the power of the test, okay? It is how often we reject the null hypothesis when it is in fact false. Coming up here. You can come see me. Okay, so that's the power of the test, and you will not have to do this. You will not have to do this calculation. But you may have to interpret it from a graph. I think that's certainly fair game. Or if you're told, for example, in the question number 25, and we're going to pick that up in just a minute. In question 25, you're given some data, and you're asked to interpret type 1 error, type 2 error, what makes the power go up, what makes the power go down, things like that. I think that those are all fair game questions. And I think it's more likely this time around because it's pretty much a no calculator test. So you don't have to do any calculations here to answer those type questions. One of the other scenarios was, okay, what happens to the power of the test if we choose a new significance level? If we increase the significance level to 1%. All this other stayed the same. The null hypothesis equal to 0.63 stayed the same. The alternate equal 0.53, 255 or 250 sample size, 10,000 simulations. The only thing we changed here was the significance level, and the power went from about 97% to about 78%. And so what that means is when we require a higher significance level, then we will commit type 2 error a little bit more often. The type 2 error is the right-hand side of this graph, where you don't reject the null hypothesis when it is in fact false. And so you'll notice that the power goes down, so you commit that type 2 error more frequently because we required a stricter test here. Okay. And we're going to come back to this in just a minute. The next question was, okay, what happens if you take fewer samples? If you're in a hurry and you go back to the 10% significance level, and everything else is the same, but you take a smaller sample size, well, power goes down again. I'm not so worried about the amount or the value here. I just want you to get the qualitative notion here of what's going on. When sample size goes down, our ability to detect a difference between the null hypothesis and the alternate is reduced, and we're going to commit type 2 error more frequently. So the probability of committing type 2 error, if you remember those formulas, it's 1 minus the power. So that would be about 24% of the samples would cause us to accept the null hypothesis, when in fact the proportion is in fact less than 0.63. So as the sample size goes down, the power decreases and the opportunity for committing type 2 error increases compared to our base case. One last scenario we looked at was what if we kept everything the same? The null hypothesis was the same, 250 sample size, 10% significance level, but we said the alternate was 0.50. In other words, our the true value of the new population is farther from the null hypothesis. What happens in that case, the power goes way, way up, because we're able to see the bigger difference between 0.63 and 0.50. We're able to detect that bigger difference easier with a 250 sample size and at the 10% significance level. So as the difference between the null hypothesis and the true value increases, the power goes up, and to the point where we almost never accept the null hypothesis when in fact it is false. And in fact, there are only out of the 10,000 samples, only 29 or 21 of them would have caused us to commit the type 2 error. So the other quantitative analysis that we might do here, qualitative analysis that we might do here, as the difference between the null hypothesis and the true value increases, the power goes up. In other words, it gets easier to see a bigger difference. And so we're less likely to reject, fail to reject the null hypothesis when in fact it's false. And so let's go back to the base case here, where null hypothesis was 0.63, our alternate 0.53, 250 sample size, 10% significance level. That's our base case. And what we did is we changed, the first thing we did was change the alpha, the significance level, from 10% to 1%. And we noticed that the power went down. So what can we do? What do we have to do if we say, hey, I don't want to accept this power of 78% on my test. I want a 1% significance level, but I also want 97% power. I want a strong test. Well, what we have to do, the only thing we can do, is increase the number of samples. And so in order to get that power back, I have to take more samples. And in this case, at a sample size of about 400, then I got back to about 97% here, or only about a 3% chance where I would fail to reject the null hypothesis when it's in fact false. Okay, so if you insist on a high significance level and a high power, then your only choice is to increase the sample size. And that's up to you as to, do you have the time and the resources in order to collect those extra samples? So it's up to you. But that's the conclusion we draw. If we want a high significance level and a high power, then we have to take more samples. And that's really what we, the kind of the main takeaway I want you to take away from this particular example. Okay. So what I want to throw up now is, let's go back to your example in the textbook, question number 25 that we looked at for yesterday. Got to put my other glasses on so I can read the fine print, but that scenario is a drug testing situation where 10% of patients who take a new drug for Alzheimer's experience nausea. And we think that it's really less than 10%. And so our null hypothesis is that the true portion of patients is equal to 10%. We're testing against an alternate where that proportion is less than 10%. So you do the test, and you conduct the test at the 5% significance level against an alternative of the true proportion really being 0.08, and you find that the power of the test is 0.64. And so the first question is, what does it mean in simple language, what that the power is equal to 0.64 in this particular setting? And the way we would describe that is, if the true probability is in fact 0.08, then the probability of correctly rejecting the null hypothesis is about 0.64. In other words, in about 64% of the samples that we could take of this particular sample size, we would correctly reject the null hypothesis when the true value is actually 0.8. So what I want us to do here is I want us to play around and see what kind of sample size would require or would produce a power of about 0.64. Okay, so we'll take a look at the applet here. Our null hypothesis is 0.8. The true value, the true alternate value is 0.08. And just for grins, we're going to start out. I have no idea what number to pick here. I'm going to start out at a size n equals 100. And the number of samples really just tells us how many, how big of, how accurate, how close to the true distribution of the population proportion we get with our sampling distribution. And in this applet, it's pretty fast to do 10,000, so I'm just going to do 10,000. So here I am. I'm going to draw my samples. And with a sample size of 100, I want to now check the proportion of successes. And what I get is a power here of only about, what is that, 0.0895, so about 9%. So I'm really, really far from 0.64, okay? So I'm going to have to increase my sample size to improve my ability to reject the null hypothesis when it is in fact true. I've got to increase my sample size. I'm just going to pick 250. Now that means I have to redo my sample, and now you can see here's my sample, and let's see what we get. Well, we improved. We got a power of about 0.28, so we're roughly halfway there. So if 250 gets us halfway there, let's see what 500 gets us. So we'll redo our sampling, and now we'll check and see. And in this case, we've got a power of about 0.41. So at a 5% significance level, this is a one-tailed test. We're only concerned about the alternate being less than 0.1. I'm going to have to take more samples. And you might say, well, Barry, what happens if you do the sample again? And I think that's a fair question. So let's keep everything the same. We'll kind of keep this number 0.42 in the back of our head here. Let's take another sample of 10,000. Oops, let me redo this now. I guess I have to change something here for it to reset. So now let's do another sample of 10,000. Why is that not resetting? Oh, let me hit the reset button here. Now, there we go. I knew there was a way to reset that. Okay, so let's try 500 samples. We'll draw our samples, and now we'll check and see. Even if I do a completely different sample of 10,000 different cases with a sample size of 500, I still get a power level of about 0.42. Okay, so pretty consistent results. Even though I took another sample. Now I could continue to sit and do sample after sample, but I want to see what my sample size is that gets me to a power level of 0.64. And again, all I'm doing here, this is just trial and error. I really don't know what that number is. And so so there's 0.49. I increased a little bit. Okay, so I'm going to go for broke. I'm tired of playing games here. Let's take a sample size of 1,000. We'll conduct our sample. And look at there, we get a power of about 0.69, about 0.7. So we kind of overshot it a little bit. Now this will be the last one. This should get us pretty close. 0.63. Okay. So you can see what happens there if we settle on a particular value of the power, and we are committed to a certain significance level, then the only thing we can do here is increase our sample size. And to increase the power of our test, we have to increase the sample size. And so what this is telling us is in about 63% of the cases, we would correctly reject the null hypothesis when it is in fact false, and the true value is 0.8 or 0.08. Okay. So we've kind of narrowed in on our base case. Now let's look at part B. You could get higher power against the same alternative alpha by changing the number of measurements you take. Should you take more measurements or fewer to increase power? Well, we've seen that already in the example that we've done. To increase power, we need to increase the sample size. So let's just do another one at a sample size of n equals 1,000. And I guess we're going to get a power level of about 0.7, which is what we got before. Thank you, dear. We will, so to increase the power, we have to increase sample size. So for part C, if you decide to use an alpha of 0.01 in place of 0.05 with no other changes in the test, okay, so we're going to change the sample size back to 900, and we're going to change the significance level to 0.01 in this case. See what the question is, will the power increase or decrease? Well, we saw from our previous examples that keeping everything else the same and requiring a higher level of significance, the power went down. Our ability to discern the difference between 0.1 and 0.08 is decreased, and we're more likely to commit type 2 error. In other words, we're more prone to failing to reject the null hypothesis when in fact it is false. Thank you, dear. And you can see how much our power went down. It went almost half, from 0.64 to 0.34. Just by reducing the significance level from 5% to 1%. And then part D of that question, if you shift your interest from the alternative to 0.07 with no other changes, and I guess no other changes means go back to the original 0.05, and we want to change this to 0.07. So we have to redraw our samples. So what should happen? Well, the difference between our hypothesis and the true proportion increase, so the power should increase as well. And sure enough, it does. Look how much it went up. It went from about 0.63 to about 0.93. Just by that very, very minor change, our ability to discern the difference between 0.1 and 0.07 increased. And now I only commit type 2 error about 7% of the time. Okay. So that's question number 25 in a nutshell. Okay. So hopefully you had a chance to look at that before our class today, and we can use this to help kind of sort out what happens to, type 1 error is up here, type 2 error is down here. Now, one thing I need to point out is that when you're looking at a graph, especially for type 1 and type 2 error, you have to recognize what the alternative hypothesis is. In this case, the alternative was less than. So the type 1 error is going to be to the left of the p-value, and the type 2 error is going to be to the right. However, if the alternative was greater than 0.1, then this graph would be flipped over. The type 1 error is going to be over here, and the type 2 error is going to be on the left. You have to know what your alternatives are before you anticipate or interpret this graph. Now, the other question might be, what happens if this is a two-sided test and you're worried about just the alternative that it's not equal to 0.10? Well, in that case, the type 1 error will show up on both the right-hand tail and the left-hand tail. All you need to know is one side of it, and then you can multiply it by 2 because of symmetry. All you need to know is just one part of the tail and multiply it by 2 to get the rest of it because of symmetry. And then the power of the test will be in the middle. The type 2 error will be in the right tail and the left tail, and the power will be in the middle. Okay, so if you have to interpret one of those graphs, just remember, for a two-sided test, you're going to be looking at your error in both tails, left and right. Okay. Okay, so let me close that for just a minute and see if we've got any questions before we move on. I'm going to introduce the next topic briefly, and really the next topic I think is really, in fact, a little bit easier. Simply because it's a little bit more of a recipe. There's a little bit more of a pattern to follow here. So I think you'll find basically what we're going to be doing is we're going to be going through the steps of conducting a significance test for a population proportion. And then probably tomorrow, if not tomorrow, certainly Friday, we'll do one for a sample mean. The steps are about the same. The couple of things you have to pay attention to: the sampling standard deviations are different. But other than that, type 1, type 2 error still means the same thing. And so we just have to conduct the steps a little bit differently. So what I want to do, I think, yeah, oops, I didn't start them over. Let me, okay, so let's start here. Confidence intervals and the significance test. The cool thing about this is at the end of this particular exercise here, we'll see a link between confidence intervals and the hypothesis test. And quite honestly, in some regards, the confidence interval actually tells us a little bit more information than the hypothesis test. The hypothesis test only really gives us a yes or no answer. The confidence interval gives us a range of values that we would expect, and that we would expect to find the true population proportion. And so in some regards, we get a little bit more information from a confidence interval than we do a significance test. But both of them have value, and both of them are important to us. Okay, so I guess sometime last week we talked about the basketball player who claimed to be an 80% free throw shooter. So we said, okay, do 50 free throws right now and let's see how you do. He only made 32 of them, so his proportion of made shots is 0.64. And our question, the way the significance test work is, does this provide convincing evidence against his claim? So what's the claim? Well, the claim is the null hypothesis here is the null hypothesis here is that his free throw shooting percentage is 0.8. And we have evidence to suggest that it might be less than 0.8. So we're going to test that against the alternative that it is less than 0.8. Okay. And where P in this case is the proportion of free throws he makes over the long haul. Okay. So remember back in the very beginning, and this is a step that you have to make sure you carry through on. You have to check those three conditions of inference before you go and conduct this test. Okay, so what were the three conditions? The three conditions were random. The data came from a random source, that it's normally distributed, and that the data is independent. So we can't just say the three conditions are met. We kind of have to identify them and tell them how they're met. And in this case, what we would say is we'll view this we'll view these shots as a simple random sample from the population of all possible shots the player takes. Another way you could do this is just take his records, go through the scorebook and randomly pick 50 shots. And that would take a little bit more time. So we're just going to say that this is a simple random sample from the population of all the shots he takes. The normal calculation, remember, for a population proportion, both the number of successes and the number of failures have to be greater than or equal to 10. And in this case, n times p is 40, and n times 1 minus p is exactly equal to 10. So the normal condition is met. But I want to point out, when I first thought about this, I thought there's no way that we have to worry about that 10% or the normal condition being met. And we just barely met it here. If the true proportion, or our null hypothesis was 0.85, then 1 minus p here probably wouldn't have got us to 10. And so we wouldn't have been able to make that assumption. But in this case, we can. So we're going to move on. And we're going to say that from shot to shot, the outcome is independent, which has been tested in careful settings and pretty much tested. The conclusion is from the same spot on the court, under the same conditions, the shooter shot from time to time is in fact independent. So we will make that claim. And so now we can go ahead and conduct our significance test. And so the first place we start, it's almost like starting out for conducting a confidence interval. In fact, when we're done right here, we could conduct it. We could calculate that confidence interval because we have the estimate. We almost have everything we need. We need the the critical value, but we've got the standard deviation. So we're almost there to conducting that confidence interval. And don't forget, when you calculate the standard deviation of the p hat, you're going to use the population proportion, because right now that's the only thing we have. So we want to use that population proportion to calculate that standard deviation. And then if you remember, this is the sampling distribution. This is the distribution of all the possible samples of a certain size of n equals 50 with mean equals 0.8 and the standard deviation 0.0566. This is the shape of all of those. This is the sampling distribution. This is not an estimate, but this is all of the possible ones, okay? And you notice our p hat value is far over here in the left-hand tail. So that gives us a bit of a clue.
Are we supposed to be saying this?
Oh gosh, doggone it. Yes, you are. I get in such a hurry. Okay. So here's, let's see, we talked about random, independent, normal. We talked about that. Okay, so now here's the graph you should have seen on your screen. And so now we'll do our calculation. The significance test uses sample data to measure the strength against the null hypothesis. So we're always testing against this value to see if we can reject it or if we have to fail to reject it. Remember, never in your response indicate that you think you should accept the null hypothesis. Always either reject it or you fail to reject it. Okay, so the test compares a statistic calculated from sample data against the parameters stated by the null hypothesis. The values of the statistic far from the null are good evidence against the null hypothesis. And we can already see that we have a point estimator that's pretty far away. So we're kind of leaning in that direction. We wouldn't be surprised here if we reject it. Remember this test statistic. It reminds us of a z-score, where we're taking a statistic against the population parameter divided by the standard deviation of the statistic. So we're going to go back up here for the statistic and the standard deviation. We're going to use the mean of p hat and the standard deviation of p hat. By the way, this formula will be on your formula sheet. And quite honestly, I really like the formula sheet that they are providing you guys. I'll show it to you in just a little bit. I really do like it. And so probably from now on, I'm going to use that because I think it presents the data in kind of a little bit more helpful order. But in any event, so our test statistic, Z, comes out to be negative 2.83. And remember, any z-score that is greater than 2 standard deviations away from the mean, we already anticipate this being a pretty unusual event. And so what we conclude here is in our sampling distribution, the p hat of 0.64, the area in that left-hand tail is only 0.0023, I think is what that says. It's kind of hard for me to read. Or is it 0.0023? What we conclude here, when the null hypothesis is true, the test has this normal distribution. And so the conclusion that we're going to draw, the shaded area shows the p-value. The p-value is this probability that we would get a p hat as extreme as the one we calculated. Okay, so the one we calculated, or the one we observed, kind of is the cut point in the tail, and everything more extreme than that falls into that p-value, or that probability of being less than that value. So we're asking ourselves, what is the probability that z is less than negative 2.83? And using table A, we find that that's equal to 0.0023. And so if the null hypothesis is true and the player makes 80% of his free throws, there's only about a 2 in 1,000 chance that he would really make as few as 32 of 50. Whether we put him on the line and watched him make 50 or shoot 50 in a row, or whether we went back through the scorebook and we randomly picked out 50 shots, there's only a 2 in 1,000 chance, or a 0.2% chance that that would happen. Okay, and so in order to determine whether we reject or accept the null hypothesis, we have to know what the significance level is. Okay, and so in this case, we've talked about this four-step process. In this case, this might help you kind of organize your thoughts. We're going to state what we want to do. We want to do a hypothesis test at a particular significance level. We don't know yet. We haven't picked one yet. And so our plan is to check the conditions for inference. What we're going to do, compute the test statistic, which is the z-score, find the p-value, and then we're going to compare that p-value against the significance level of the test. Okay. And so when the conditions are met, random, normal, and independent. And again, in your response, you can't just say the conditions for random data, normal distribution, and independent values. You can't just say they're true. You have to make a statement about how you know they're true. Then we can go ahead and calculate our statistics, mean of p hat, sigma of p hat, the null hypothesis value for p, which we call p0 or p naught. You might hear some folks say, I've had instructors call it both ways, p naught or p0. We assume this value is correct when we start doing our calculations, and then we look for evidence to prove it incorrect. Okay, so the p-values come from the standard normal distribution. And so for a one sample z-test, here is the value we're going to use, where p hat is the observed value. We have the population parameter that we're testing, we're going to use here. This is also that same value, p equals p naught. So these three are the same value. N is the sample size. And then remember, we can do three types of tests. We can do a right tail test where the alternative is p is greater than p naught. The left tail test where the alternative P is less than P naught. And then the two-tailed test is P not equal to P naught. Now, notice what we have in the two-tailed test. Our z-score is the same here and here. Okay, so we're looking for the negative absolute value of z and the positive, or the absolute value of z, which is a positive value. And so the area in this tail, in these two tails, is doubled compared to the area here. So once you find the area on this side, then just double it, and that gives you the total area for your p-value, the total probability for your p-value. But you have to make sure that we have a normal distribution, and we also have to double check to make sure that our population, a sample, is small compared to the population. So there's a lot of things, there's a lot of steps to go through in doing a one sample Z test, okay? And so quite honestly, in just a minute, we're going to finish up here, and I'll ask you to do an exercise out of the back. We'll start with one exercise out of the back. I think what I've got here is an example to walk through these various steps, and if I remember correctly, it has to do with the potato guy again. Yeah. So you remember our potato chip manufacturer, he wants a truckload of potatoes to be fewer than 8% with defects, and so he collects a random sample of 500 potatoes from the check, and he found of those 500, 47 of them have blemishes. So we want to carry out the significance test at the 10% significance level. So what do we conclude? Okay, so now we're going to go through all of those steps. So first step is always to state the significance level, the null hypothesis, and the alternate. And remember, we're looking at, we're only concerned if the proportion of blemished potatoes is greater than 0.08. So we're going to do a right-tailed sample where P is greater than 0.08. And so if the right conditions are met, we're going to do the one sample Z test. Is it random? Yeah, we're told that he takes a random sample. Is our sampling distribution normally distributed? Then assuming the null hypothesis is true, n times P is 40 and n times 1 minus P is 460. Both of those are greater than 10, so we can assume that we have a normal distribution for our sampling distribution, or a normal shape to our sampling distribution. Are they independent? Then we are sampling without replacement, so we need to check the 10% condition. And so we have a truckload of potatoes. It makes sense that if we're taking a sample of 500, it makes sense that there are more than 5,000 on a truck. That might be a little bit difficult to envision, whatever scenario they give you, but hopefully it'll be obvious. But if it's not obvious, just use this kind of get out of jail free statement, and it seems reasonable that there are at least 10 times our sample size number of whatever in the population. So in this case, the population is the shipment of potatoes. Okay, so now we'll calculate our p hat value, 47 divided by 500, 0.094. We're now ready to calculate our test statistic. Here's P hat. In this case, here is P naught for the test statistic, 1 minus P naught, n equals 500. So we get a z-score of 1.15. Always draw the picture. And so, I mean, we've drawn this picture 100 times before, before Christmas when we were first learning to do our calculations. So our p-value is equal to the probability of being in this right-hand tail to the right of a z-score of 1.15. So what we're looking for is a probability that z is greater than 1.15. So we look up 1.15 in table A. We have to take the complement of that, and we come up with a probability of 0.125. Or if you remember, you can use the normal CDF calculation on your calculator. You might get a slightly different value here, but it won't be significantly different. So our p-value here is 0.125. 0.125, yeah. Okay, so now we have to ask our question, is that significant compared to what our significance level is? And remember, we said that we were going to use a significance level of 10%. And since our p-value is greater than 10%, we fail to reject the null hypothesis. So there is not enough information to conclude that the shipment contains more than 8% blemished potatoes, and so we'll accept the truckload and start making chips. Okay. So that's the process for a one-sided test. Okay. The two-sided test, the steps are the same. It's just that we have to look at both tails to get our probability. So this is enough for us to chew on for today. So what I want us to do tonight, let me make sure which one of these I wanted us to do. Yeah, here we go. We'll just do on page 562 of your textbook. You want to do exercise number 41 about better parking. A high school makes a change that should improve student satisfaction with parking situation. I don't know if you've got bad deal with your parking or not, but exercise 41, and I'll put this in our post here in a little bit. So I will also send you these slides, and quite honestly, the outline that they give you in the slides is quite good. Quite honestly, though, these steps are in your textbook. If you'll flip through, we're now looking through section 9.2 in your textbook, and so if you'll look at about page 552 of your textbook, then these steps are here. And so, but just so that you'll have them, I'll go ahead and attach these slides as a PDF to the assignment. But exercise number 41 on page 562, we'll go over that tomorrow at the beginning. Make sure everybody's got a good handle on it. What I'll probably do is I will right before class, I'll post my solution and put it up on the screen and kind of walk through it tomorrow. Okay, so thank you guys for being patient with me. This is a long class today, I know, but we just got a lot to get through here. But quite honestly, I always felt more comfortable as a student when I got to this process of doing these significance tests, because it's more about just following the steps than it is. And once you get into following the recipe, it goes pretty quickly. Okay. Any questions here? And I can tell by the look on Riley's face, she looks like she's been drinking water out of a fire hose. So I know it's time for me to stop. And Ann Thomas is handing everything on my table to me one at a time. So that's also time for me to stop. So we will, I'll see you tomorrow. Do y'all have any questions? Skylar, you got a question? You're good?
No, I'm
Okay.
good.
All right. We'll see you tomorrow. We'll be back at 1 o'clock tomorrow. Y'all have a great rest of the afternoon. We'll see you. All right. Bye-bye.
You too. See ya.
Girl, will you stop? Will you stop? Put it back in there. Put everything back in there. This is where it goes. Okay? Goes right there.